Well, we're pleased to have as our colloquial speaker today, Hiroshi Nakajima from RIMS in Kyoto, and his title is the AGT conjecture.
Thank you very much for introduction. I'd like to thank Simon Center for invitation and giving me an opportunity to talk here. So the title of my talk is AGT conjecture. So AGT conjecture lies in the intersection of geometry and physics. So that's the reason why I choose this topic to talk here. So first of all, I want to explain, before going to talk, I want to explain why I'm excited on the AGT conjecture. So I know so many people are excited with this AGT conjecture. It's a very interesting topic, I think. But for my personal point of view, it is interesting by the following reason. So I obtained some results about 10 years ago, which I will explain later. But I could give the proofs for these results. But somehow I was not so happy with the proof, because the proof doesn't really give the actual reason why such a result holds. So somehow I can give the proof, but I still somehow puzzled with this result. And then some AGT conjecture comes later, and this AGT conjecture comes later, and that AGT conjecture is still conjecture and doesn't have mathematical foundation yet, but it certainly it gives the clear explanation of my old result. That is the reason why I'm excited by AGT conjecture. So I'm going into the talk. So, but I slightly change the order of the history, and I first explain a physical background a little bit, and then I will explain my old result. So AGT conjecture comes from a certain six-dimensional theory. And this six-dimensional theory is coming from string theory. So I will explain a little bit about it. So let gamma be a finite subgroup of SU2. So it is well known that this is classified and corresponding to linking diagram of type ADE. So in particular, you have the corresponding Lie algebra, which I denote by G gamma. So I consider six-dimensional theory, which is obtained by reduction of so-called type 2B theory. So reduction, so physicists usually called compactification. So I consider the quotient space C2 divided gamma, and I compactify the type 2B theory on this space. Then you get the six-dimensional theory. So this is the so-called 2, 0 theory in the physics literature. So I will not explain what this theory is, and anyway, so I can't. But this is a six-dimensional theory. So if you have a six manifold together with some Riemann metric, then
Six is 1, 1 from like strings or something, and then plus the 4 there. Is that what it means, the 6?
6 is just comes from 10 minus. This is a 4-dimensional space, so this is just the 6 is 10 minus 4. I don't mean any further meaning so far. So once you have a 6 manifold, and then by considering partition function, you get So this is the partition function. So you get the number, complex number. So you consider this is some kind of function on the space of Riemannian of the space of six-dimensional manifold, Riemannian manifold. And partition function is you just imagine that you consider the functional path integral over the space of some fields on this six manifold. But unfortunately, it's known that this theory, six-dimensional theory, doesn't have Lagrangian description. So such kind of naive understanding of this partition function is not possible in here. So you just imagine that there's some way to assign number to six manifold. And sometimes I also put four manifold in four-dimensional submanifold in M4, which I consider those fields on six manifold has the singularity at those four manifold, and you put some gauge kind of gauge field on this four manifold, which describe the singularities of fields which I'm considering. But still, I mean, those are very vague because, as I said, so this theory doesn't have Lagrangian description. So it is still, again, some vague sense. But I accept such a kind of such theory exists. Then now I consider the following special kind of six manifold. I take two-dimensional Riemannian manifold, and with some punctures. Then I take M to be C times X. X is a four manifold. And D is just X union of Xi times X. Then, so this theory, G gamma. So I fix this data. Then C and this Xi times this. I move the four manifold and gauge field. Then this gives a number. So this is an assignment of numbers to this four manifold plus gauge field. So in this way, starting from six-dimensional theory, so this and fixing these two manifold functions, this gives a four-dimensional quantum field theory. So we put this the so-called topological twist on this six-dimensional theory. Then the resulted theory is the theory depends only on. So usually the quantum field theory depends on the choice of Riemann metric. But here depends only on the, first of all, on the dependence on the C. It depends only on the conformal structure or holomorphic structure on C and more precisely C plus punctures. And also, for the four manifold side, it depends on the topology, or more precisely, differential topology on X. Depends only on that. So in that sense, so I get fixing C and punctures, I get topological quantum field theory. So four dimension topological quantum field theory. But on the other hand, I can reverse the role of two manifolds and four manifolds. So if I start with four manifolds, so this is a four manifold. Two.
Why do you say you get four-dimensional? The twist is only done in the Riemann circle.
Well, it is a little bit more complicated. So you must do twist in 6 dimensions. Okay. This
different from what AGT did.
Something different. I'm not so familiar with physics literature, but so anyway, kind of yeah. I don't want to go much detail about this because I don't quite understand. So anyway, so the result, I just want to say the result theory depends on the conformal structure and the topology. Then you get, if you start with a four-dimensional manifold, then you get two-dimensional conformal field theory. Well, so far it is not specified. I mean, later I will take X to be non-compact. But this is some general philosophical framework. So in various situations you must modify a little bit, but it works either X to be compact or non-compact. So I give you example. So take C to be torus with period tau. Then the theory, without the punctures, you get some four-dimensional topological quantum field theory. So this theory is known, and this is so-called n equal 4 supersymmetric gametes theory. For gauge group. G gamma, which correspond to which is simply connected to Lie group correspond to the Lie algebra. So after topological twist, this theory is this theory computes something like following. So you consider on the four manifold, you consider the moduli space of G gamma instantons. So this is moduli space. By the way, I should say that after topological twist, this four-dimensional TQFT, if you change the gauge field, this four-dimensional topological quantum field, and we usually want to integrate over the space of all connections, but after topological twist, the integration is localized to the modular space of instantons. So in that way, so after topological twist, modular space of instantons appear naturally from here. So I consider the modular space of instantons on X with instanton number n. Then this partition function is the generating function of the Euler number of these just Euler generating functions of Euler number of the instant moduli space, and this Q is related to the period of the torus by the usual formula Q equal exponential of 2 pi tau. So from this construction, so this theory, as I said, this theory should depend only on the conformal structure of C. So C with tau, period tau and C with period minus 1 over tau is as a complex manifold, this is isomorphic. So this means zeta for tau and zeta for minus 1 over tau is equal, but in fact it's not exactly equal. You must have some correction, like in the case of some powers of Q, like in the case of modular form. So this G, so this G should be modular form.
Can you say where the correction comes from?
So usually, so this power depends on the topological data of the original form manifold. Usually something like the Euler number of the form manifold X.
Is that for the six-dimensional theory? That's the partition function for the whole six-dimensional theory?
So six-dimensional, and I just take C, this C cross this M. This is C cross M to be C cross X.
It's just for the torus. Is it just for the?
This is just only for the torus.
But it's a 4D TQFT, right?
Yes, I choose C to be torus. Then I consider six-dimensional theory for C cross X. Then I get this theory. And this conjecture, this was in fact conjectured by Pfaffer and Witten in 1994. And this conjecture is my first encounter with physics. So now I come to the point where I explain my old result.
So this Euler characteristic is supposed to be the open moduli space or something?
Well, so that is, in fact, mathematically this is a serious point. And usually I only consider moduli space X to be complex surface, and I usually consider the moduli space of torsion-free sheaves instead of actual instant moduli space. That is supposed to be a kind of resolution of Uhlenbeck compactification, and still, I mean, we don't have satisfactory mathematically rigorous understanding of Euler numbers for general form manifold. What?
Because you don't even have the space that it's supposed to be the Euler characteristic of, because you don't have the analog of the Giesecke moduli space?
No, I don't know. So, but so I take X to be special form manifold. So I take X to be C2 divided by, again, finite subgroup of gamma, so finite subgroup of SU2. But I take another subgroup, so I denote gamma prime, and I consider its minimal resolution. So this is sometimes called a Lie space. Then I proved in 92, slightly earlier than this. I consider the middle dimensional cohomology group of the instant moduli space for the when the gauge group is unitary group and N. And I take the sum over all instanton numbers. So this gauge group appears correspond to the first choice of the group gamma. So this UK, I mean, for precisely I must consider SUK, but for this result, it's more natural to consider it as a UK. So I'm a little bit confused about it. But anyway, so this means that the gamma is roughly correspond to a type of type AK minus 1. So this, I want to emphasize that this gamma and gamma prime are different. Then I construct a structure of integrable highest weight representation of affine Lie algebra for G gamma prime. And its level is equal to K. So in particular, if so the Euler number for this modular space is not, in some sense not well defined. But if you believe that, so this, for example, if you consider L2 Euler, if you consider Euler number in the L2 sense, maybe the middle dimensional, middle degree cohomology group, only middle degree cohomology group contribute. So then. This, if you believe Euler number, maybe in L2 sense, of M of UK of N, and take sum. So this is just counting the dimension of this modular space. This is basically character of this representation. Of this representation of affine Lie algebra. And the modular invariance of the character of affine Lie algebra is well known. So which is proved by Katz and Peterson in 1984. So somehow this results for affine Lie algebra can be reproduced by this 6-dimensional viewpoint. And also if X is a complex surface, and I consider the Hilbert scheme of points on X. So this is a kind of a modular space of U1 instantons with instanton number n. In strict sense, U1 instanton just consists is just a line bundle. But if you allow some singularities, so Hilbert scheme of points is a nice replacement of this instant modular space for U1. Anyway, so in this case, if you consider the Euler number of Hilbert scheme and take the sum over n, then this was computed by Getche, and the answer is the infinite product 1 minus q to the power d by 1 to the power Euler number of x. And this is a kind of Dedekind eta function, and you have a modular invariance. And I and also independently by Gloinowski in 94, we constructed the structure of the modules of the Heisenberg algebra. So this is a module of affine Lie algebra which corresponds to G in some sense affine GL1. So this is Heisenberg. And this Dedekind eta function is just a character of the Fock representation of the Heisenberg algebra. So these are the results which I proved. But the proof is just so those affine Lie algebra or Heisenberg algebra are given by generator and relations. So I just define, I just introduce some sub-variety in the product of two modular spaces, which correspond to generators for these algebras, and I check the defining relations. So that is okay, but somehow I don't. There is some vague reason why I should choose such generators, but I don't have any clue why defining relation is satisfied. And And anyway, sometimes I must change the definition of generators slightly. So the proof is somehow try and errors, and I'm not really satisfied because I don't see any reason why such result hold. So that is what I explained at the beginning. So the better viewpoint so I again return back to 6-dimensional picture, and so I fix X now, and I change this two-manifold sigma. So I consider this as a two-dimensional conformal field theory. And then I use Seagal's axiom for axiomatic approach to two-dimensional conformal field theory. So if you have Riemann surface with punctures, so by conformal change, you can consider this as a Riemann surface with boundaries. And then in the axiomatic approach, so you assign to close two manifold, you assign numbers, and for boundaries, namely this S1, you assign maybe what I do. I just from now I just write this to be some t. Maybe I just write z. So this z of z. So z is the conformal field theory. So to a boundary, you assign a Hilbert space. So this is some quantum Hilbert space. And if you have a two manifold with boundary like here, then you assign a vector. So GC is a vector in the boundary of C. So this is 8. And if you have several boundaries, then it gives just a vector in the tensor product. So this is the axiomatic approach to the two-dimensional conformal field theory. And so recall that to reproduce the Euler number, we consider the torus. And for the two-dimensional CFT, it is well known that for torus, Z of Z of torus is just this character. So again, I took the generating function with respect to Q. This is the character of this H. So this means if this X is equal to C2 over gamma prime, tilde, and gamma is of type AK minus is 1. So this, my result says that the Euler number is a character of the representation, which means for this, what this just means H should be this representation of affine algebra. Then for other Riemann surface, I mean, there's natural framework which fits with this representation theory. So it is well known. So the corresponding CFT for general Riemann surface should be just the West-Zumino-Witten model. for this G gamma. So of level. For these data. So this gives not only gives an explanation of my old result, it certainly gives me a direction to which I should go. So I should consider the what is really more mathematically I should try to reproduce this theory by something considering instanton some data from instanton modular space. So this is, I think, nice point. Yeah, no, I should come here. What time? And also this is a side remark, but it also says something interesting, I think. So recall that this six-dimensional theory was constructed. I mean, I didn't explain the detail, but so it was six-dimensional theory was constructed by compactification of type 2B theory on C2 divided by gamma. And then I again compactify this theory to get some theory with two-dimensional. I compactified with. I mean, this is I take resolutions, but I just confuse those whether I take resolution or not. So these two spaces are very similar. So from this viewpoint, natural to expect. Symmetry exchange gamma and gamma prime.
So this is 10-dimensional theory?
This is a 10-dimensional theory, and I compacted by 4 manifolds to get the 6-dimensional theory, and then further compact by 4-dimensional theory to get the 2-dimensional theory. So it's a little bit technical detail, but so this. In my theory, so this K minus gamma prime determine the real algebra, and this first gamma determine the gauge group, and which turns out to be determine the level of this. So unfortunately, I cannot replace this by other groups. Because remember some technical detail that the instant modular space I usually use algebra geometric technique, and for other group it becomes more hard to analyze the modular space. So I assume both gamma and gamma prime to be type A. Then but the order of the cyclic group may be different, and so changing gamma and gamma prime means I change the ordering of the cyclic groups. And in the affine real algebra, so this gamma prime determines the rank of the group, and this first gamma determines the level. And if I exchange the role of two cyclic groups, I get this. From this, I get so-called level rank duality, which is well known in the representation theory of affine algebra, which was found Igor Frenkel in 80s. So for other groups, I don't know how to interpret, but somehow this consideration suggests that you should have some symmetry between gamma.
Why did you have to restrict to A at this point?
Yeah, that is a technical point. So I must assume the gauge group to be of type A because I use algebra geometric technique. But even if you go to the affine real algebra, it is somehow clear that if you go to the other groups, so this level, I can consider level to be integer, but I can't consider level to be some type D or something like that. That doesn't make sense. Level level is just the powers of line bundle on this modular space of bundle of curves. So level must be integer. So if you really, if I want to extend to other types, then some more exotic things should be introduced.
Can you state a conjecture? What would be true though, if you were?
No, I have no. Maybe you must really need to use this two-dimensional CFT language instead of considering affine algebra. Okay, now I come to state AGT conjecture. So I take X to be R4. In some sense, this is the most trivial form manifold, but instead of just considering this as a topological manifold, I consider torus action, a two-dimensional torus action. So this torus action plays something like a low load of Riemannian metric on R4. But as I said, so this theory is a topological quantum field theory. It should not depend on the metric at all. So after some slight modification, this theory depends still on this action. And gamma is a finite subgroup of SU2 as before. Then again, I want to consider the modular space of G gamma instantons on X. I again consider the homology group. But here, instead of just considering the middle degree cohomology group, I consider all degree cohomology groups. And I also consider the equivalent cohomology groups. Here you have a natural action of T2. So this comes from the T2 action on the base. And also there is natural action of G gamma. Maybe G is fixed, so G. So this modular space is so-called modular space of framed instantons. So there's the flame change naturally acts on this space. So again, I want to consider this to be the quantum Hilbert space H. Of some conformal field theory. And AGT just gave the answer, what is this, the conformal field theory. The CFT for this X, for X and gamma, is the one associated with the so-called double algebra. So double algebra is determined, is defined for affine algebra. And I don't want to give the definition of double algebra, but just recall that for if G gamma is affine SL2 hat, then this double algebra is Virasoro algebra. So double algebra is some generalization, higher rank generalization of Virasoro algebra. So this is the AGT conjecture. And in particular, this leads us the following conjecture. This, in particular, H. So this is a well-defined mathematical object. H is a representation of of this double algebra. And this double algebra is an example of vertex operator algebra, and there is no presentation by generators relation like the case of Virasoro algebra or Heisenberg algebra or affine Lie algebra. It is defined by the so-called Drinfeld-Sokolov reduction. But anyway, so this is mathematically rigorous object, and this statement, H is a representation of double algebra, is a mathematically precise statement. And in fact, this theory has a slightly different flavor than the theory which I just explained here. In here, you only have finitely many irreducible representation of affine Lie algebra of level k. But here you have irreducible representation of double algebra have continuous parameters. So this is this Wess-Zumino-Witten is so-called rational conformal field theory. This is irrational conformal field theory. So from mathematical point of view, so this conformal field theory is not studied so much. But anyway, so there's a continuous parameter, but the continuous parameter naturally from this geometry. So maybe I should write this. This has the representation has parameters called the central charge and the highest weight, and both are determined from this equivalent cohomology of T2 cross G over a point. Because this equivalent homology is a module over equivalent cohomology over a point, so this is a module over this, and this is a polynomial ring. So for T2 you have two parameters which usually denoted by epsilon1, epsilon2, and for G you have parameters corresponding to rank of G, and you take the invariant invariant part of the while group. So those epsilon1 A's and epsilon1, epsilon2 and A's appears as parameters in the representation theory of double algebra. So this is irrational.
A's are acting as they multiply. I mean, they're operators in the Hilbert space.
Yes. So this
become these parameters. You specialize to given values.
Well, so I can consider variable as a parameter also.
Yeah.
So people usually consider some specialization of this representation, and at some special parameter, representation theory becomes interesting. But for generic parameter, the representation theory are boring. So that is some kind of general feature of this kind of theory. And so anyway, here, but I consider those variables to be variables or parameters in the theory.
Is this space related to the Hilbert scheme of the ALE surfaces? Or?
No, I'm just taking X to be R4.
Just to be R4.
Just to be R4. And maybe so for the Hilbert scheme of points, I take double algebra for, it doesn't literally make sense, but the double algebra for U1 or GL1, that is nothing but Heisenberg algebra. So in that sense, I recover my old result. But
So is this the special role of AK in the previous story somehow related to the fact that you can choose those to be toric hypertailors?
Or is this just a
No. So it's nothing to do with the toric hyperkera. So this modular space is a modular space for instantons, but for type A, modular space for instanton can be identified with modular space of vector bundles, stable vector bundles. And I just replaced stable vector bundle by torsion free sheaves, stable torsion free sheaves. Then there are lots of geometric machinery to study them. That's the reason why I must take the group gamma to type A.
This instanton modular space here, is this partially compactified in any way, or is it just?
Well, I think this is a little bit vague. I first consider the partial compactification, the so-called Uhlenbeck compactification, and then I need to replace this cohomology group by intersection cohomology group. So then this conjecture becomes more precise conjecture. But for type A, you can consider the modular space for torsion free sheaves instead, and then it is a smooth space, and you don't need to consider the intersection cohomology groups, and you can just consider ordinary cohomology group. So that makes everything much simpler. So anyway, so this conjecture. Well, I should say this is not really AGT conjecture. AGT conjecture really expect some conformal field theory associated with this kind of attached with this data. And I only talked about this H associated with torus. So this is this is a kind of small part of the AGT conjecture. So this conjecture. Sorry. So this is 3 names. 3 physicists. Alder, Guy, Otto, and Tachikawa. By the way, all the physics I learned and I talked today is I taught from Tachikawa. So I hope I understand well. So anyway, so conjecture is proved for type A. So this is due to Moriko-Kunkoku. So it's two independent proofs. So in the remaining 10 minutes, I would like to explain the key ingredient in their proof. So here I first fix the group gamma from the beginning, but the point in the proof is called the change gamma. Or more precisely, you change the gauge group. So instead of G, in this case, just the general linear group over special linear group. So you consider that, but I want to explain so that the framework can be extended to arbitrary groups. So I consider the Levy subgroup. So this just since this is of type A, so you just this block diagonal matrix. Then
excuse me, in the conjecture, what does H mean?
H.
Something is a representation of this.
H is this equivalent cohomology of instant modular space, and take direct sum of.
But that is a representation, isn't it? Or is that the conjecture?
That is the conjecture.
Oh.
That is the conjecture. And that comes from the general philosophy that is this 4-dimensional manifold should give the 2-dimensional cohomology field theory. And for torus, you get this Hilbert space. Then you consider the moduli space of G instantons with instanton number n, and you also consider moduli space of L instantons with instanton number n. And then and also I choose parabolic subgroup, corresponding parabolic subgroup. Then choice of this gives some LP of n. So this is a Lagrangian. Lagrangian subvariety in the product. By the way, so this instant moduli space is a hyper-Kähler manifold or holomorphic symplectic manifold. And I choose a particular complex structure to consider to be a holomorphic symplectic manifold, and there is some Lagrangian subvariety in here. So roughly, this is given by, if I use the algebraic geometric definition, so this corresponds just like, so if you have G bundles, so this moduli space, this instant moduli space is moduli space of principal G bundles, and so you have a sub variety of which can be the bundle whose structure group can be reduced to P bundles, and L is a quotient. Levy subgroup is a quotient of a parabolic subgroup. So you can assign L bundles from P bundles. So you have two maps from P bundles to the product of to G bundles and L bundles. So this inclusion is given by that. Then I consider this as a correspondence. So you have the map of instant moduli space. In fact, it is more natural to consider all direct sum. So if you have some cycle in here, then I put back to the product and take intersection with these Lagrangians, and then push forward to the second factor. So this is the space H associated with G, and this is the space associated with L. And so we want to show that this HG is a representation of double algebra, and we want to also show that this is a representation of double algebra for L. But if I take L to be torus, maximal torus, then the corresponding double algebra is, so it is product of just C stars, GL1s, and the corresponding double algebra is just the tensor product of Heisenberg algebra. And the number of copies is just I equal 1 to rank of G. So this is basically just the product of Hilbert scheme of points. So on here, this H of L is a representation of this double of L, G of L hat. This is already established. So it means this representation of double algebra can be realized in the representation of double algebra representation of this Heisenberg algebra. And that kind of realization is known in representation theory. Representation in this. So the representation is correspond to Heisenberg is a Fock space. So this is known. This is due to Edward Frenkel and Fagin-Frenkel. So by also considering a slightly, so not only the torus, slightly larger Levi subgroup, you can check that this realization is the same as the one which is given by Fagin and Frenkel. So in this way, you can show that this double algebra, this HG has a structure of the representation of double algebra. And I hope this framework can be, this framework is general, so works for arbitrary group. And so the only things which we must check are of technical nature, and I hope to give the proof for this conjecture for arbitrary group in near future. So thank you for attention.
I don't know what I'm talking about, but this reminds me of something called the Virasoro conjecture and Gromov-Witten theory. Is there any connection?
Oh.
The algebra's generalization of the Virasoro algebra says some representation exists.
Yeah, so sometimes.
It has a physical motivation too.
Yeah, that is somehow for physics. I think it's far away, and this Virasoro conjecture comes from matrix models and such things. And so from this this instant modular space, you can define the so-called necklace of partition function. That is a cross cousin of Gromov-Witten invariants, and somehow that is. For SL2, that can be understood by the representation, using representation of Virasoro algebra. For SL2, so this modular space is a representation of SL2, Virasoro algebra. So that maybe somehow can be considered analog of this Virasoro conjecture.
Questions? Yes.
If you have a surface with bound, then the CFT should assign you a vector in the Hilbert space.
Yes.
So it should be some homology class on that modular space. The Hilbert space is the homology.
Yeah.
So what is this homology?
Well, so that is the next step of, next step from this conjecture. And in some cases, that is given by the Euler class of the tautological bundles. I think it is for Riemann sphere with 3 punctures, and you put some condition on one of the 2 punctures. And but in general, I still don't have any clue of what is the cohomology class associated Riemann surface with punctures.
Test is across the way now.
Yeah.
The next box is 2.